So last time we talked about terminal and initial objects for the first examples of something defined via the relationship, or the first example of an object in a category defined via its relationship with other objects in the same category. So this is an instance of a certain kind of definition called universal property. And today we're going to see two more examples. So we're going to talk about products in a category. So here's the definition. Given two objects in a category A and B, well, two objects in the category C called A and B, product of A and B consists of some pieces of data. So first of all, an object that we call A times B in C, and morphisms from A times B to A, and then call pi A, and from A times B to B, I'm going to call pi B, such that we have the following properties. So the property is going to be a bit complicated, but we need to start with an arbitrary object in the category. So such that for any arbitrary guy Z. And now let me point out that I use the also for the arbitrary guy in the definitions of terminal object and initial object yesterday, so I will try to be consistent with that. So for any Z in the objects of C, well, I have some more stuff. And morphisms in the diagram I'm about to draw. So we assume that we have some Z, and then we assume that we have some guy here, and then we call this curly Z of A and curly Z of B. So we assume that we have this data. So the object Z and two morphisms, Z's of A and Z's of B. And we know already floating around we have this data, so I will just add that to the diagram. So we have the object A times B, and the morphism here pi A, and the morphism here pi Z. Okay. So for this data, all this data, or for this part is already guaranteed from up there. So for this data, we have a morphism. Let me call it U sub Z from Z to A times B. So now I put that in the diagram. Here. Making the diagram commute. Okay. This is going to be a complicated definition. But let's think, first of all, about some examples. So what do you think the product is in the category of sets? Maybe the notation is a bit suggestive, and then we just check that what we think satisfies the definition.
Pairs of Cartesian products.
Yeah, the Cartesian product. So, okay, so we call it the Cartesian product usually. Also, this product, we often call the Cartesian product just in a general category, because if I have time, maybe at the end of the lecture series, I will talk a little bit about models, categorical models of linear logic, which have products that are not, that are a little bit of are a little bit less well behaved than this kind of product. So this kind of product we often call it Cartesian product, just to emphasize that it's this one with the universal property. Right. So instead we have the Cartesian product. So just to remind you, probably everybody has seen this, but instead the Cartesian product is defined to be the set of pairs. So we have a set A and a set B. The Cartesian product is a set of pairs coming from A and B. Okay, so let's check that this Paige set satisfies this definition. I'll just talk through it. Okay, so we have the first thing, an A times B, or any A and B. What are these morphisms, pi A and pi B? Yes. Yeah, projection. Projection is a good word for it, but explicitly, what do they do? Yes.
You build a set convention for just to take down the A's.
Yeah. Yeah. So pi A. It goes from A times B to A. Taking a pair like this, and we just spit out A. And pi B is the same. Okay, so we have these two morphisms. And what about this complicated thing? So let's think about it. If we have another set Z, and a morphism, or a function now, we're in a category of sets, a function Z sub A to A, and Z sub B to B. We have A to B here, its projections. How do we find this map? Again, draw it in purple. Yes.
Lambda z dot the pair of za z zdz.
Exactly. Okay, that's what this purple guy should be. Wiggly arrow. Okay, yeah, so we have, we need to take an arbitrary set Z that we know how to turn into A's and turn into B's, and we need to figure out how to turn it into a pair of an A and a B. So indeed, we take a little z here, and we just make the pair of these two functions. Yes?
Is the product unique?
Yes, yes, exactly, that's going to be the next thing. So we verified inside here the Cartesian product. Let's think about prop. We'll come back to type stuff at the end of the lecture. So let's think about the category prop. What do you guys think the Cartesian product is? Yes.
Conjunction?
Conjunction, exactly. So we have conjunction of this. So let's check that it satisfies the definition. So if we have two arbitrary propositions, two arbitrary objects of our category propositions, we certainly have a new object, a new proposition. Let's say we take two propositions, P and Q, and then form a new proposition, P and Q. So the and is the times there. And what are the morphisms, pi A and pi B? Yes.
like the sort of like elimination rule for and?
Exactly, the left and right elimination rules that tell us that if we know P and Q, then we know P, and if we know P and Q, then we also know Q. Okay, so we don't really have to give these a name because in the category prop, remember is thin, so there's at most one arrow given these two guys, right? So there's a thin one. We gave it a name. Okay, so that's all the data that we need. And now, let's think about the diagram. There we got it. So if we have another proposition Z that implies P and implies Q, is it true that it implies P and Q? Yeah, that should be derivable with whatever rules you use to define your basic propositional logic. So indeed you have the implications, the arrow. Yes?
Can you explain a little bit more what you said is in the set?
About what?
You said about
Yeah, so it's this arrow here that I'm defining using lambda notation. So all the data tells us that we know how to take an element of Z and produce an element of A via this function. And we also know how to produce an element of B via this function. So we take an element of Z and we return the pair of the A and B that we get with these two functions. So yeah, we can write it like that. Okay. Yeah, so these are two good examples. Like I said, we're going to return to the category of types probably at the end. So then, like someone asked, we can indeed show that the product, is unique. So, this is an exercise for you because the logic is basically the same, so it'll be a little bit more complicated because the definition is more complicated. But otherwise, the logic is the same as the proof for terminal and initial objects. So here's an exercise. Show that the product A times B of objects A and B in subcategory is unique up to unique isomorphism. Maybe can someone tell me already how they would start to produce the two maps between, like, let's say, A times B and A times B prime or something that are both products that we need, and we need two maps into something using their isomorphism. What do you think? Yeah.
By the universal property, like since they're running by hypothesis, these two different things are both products, so they have to take care of them.
Yeah, so in terms of this definition, so last time when we talked about terminal objects, we were saying that something is terminal if there's exactly one arrow like this. Oh, I forgot a word here. Okay, we haven't talked about it yet, but let me just make this more precise and say unique. So we have a unique morphism here, just like in the definition of terminal. Otherwise, this would be called a weak product. Yeah, so maybe it's an exercise for the listener to verify that these two arrows are unique. Yeah.
Two questions last. Without unique there, then you wouldn't be able to do that.
No.
Okay.
There would be arrows back and forth, but they wouldn't necessarily form an isomorphism that would be unique.
And the second question is only some categories have some products, right?
Yeah, exactly. Just like we saw last time, that some categories have terminal objects and some don't. So this is the data that we start with. Like, so you're given this stuff, and you say, if you can find this other stuff, then we have this unique map. Okay, great. So like with terminals, we had, we said that that maps like this are unique. So that if we had two terminal objects like T and T prime, we put the T prime here for Z, we find a map like this, and then we did the other thing, switching T and T prime intervals, then we find a map in the other direction, and we showed up connecting both of them. So here, if we have our product A times B, if we have another guy who also claims to be the product, A times B prime, let's say, then we can put it in for Z, just like in the proof for the terminal objects. And it will have to come with projections if it's pretending to be a product. So it will have two maps like this, and then we will get a unique map from one product to the other product. And vice versa, and the proof continues the same way for terminal objects. Yes?
Are the pi morphisms, those are unique as well, or not necessarily?
It's part of the data,
Okay.
so yeah, it's part of the data. I mean, certainly, like, if you have in set, I don't know, the booleans times booleans, so 2-element set times 2-element set, or the 4-element set, you have two projections here. But they're definitely like more maps from the 4-element set to the 2-element set to this one. Yeah, I guess there's like 16 maps from the 4-element set to this one. Okay. So, right, so here's an exercise, show that products are unique. And now I want to give an alternate definition to the one that I gave here for products to connect it with the notion of terminal object. Yes?
If you have more than one map from Z to A and Z to B, doesn't that allow you to construct more than one map from Z to A cross B?
Yeah, absolutely. So when I say unique here, I mean unique with respect to the data that I put in, which is these three things, such that it makes the triangles commute. So it has to commute with this guy and this guy. So certainly, like, if these are sets and they have more than one element, then there's going to be like many, many maps that you could come up with, given a particular Z. So for the two maps that you choose, there's going to be a unique map here that makes both triangles commute. Yeah, so by choosing different maps here, you're going to get different maps here. Yeah. Okay, so here's an alternate definition. Let me write it over here. Okay, so I want to consider again two objects into the category C, and I'm gonna redefine the notion of product. And it's gonna be an exercise for you guys to show that these two definitions are equivalent. So we have two products, A and B. I'm going to define a category C, A, B to be, or to have objects. So we want to have objects. So maybe let's look at this definition real quick. So in this definition, we have in the first two things, an object, B times B, and these two maps. So ignoring this part, we have this particular shape, which is called a span. Not very important to know the word span, but I might say it a few times in the next minute. So we have this thing, these two arrows, which is a span. A span is something with one object at the top and two arrows coming out, and two objects here. Okay, this thing that we plug in to this property to get out the U is also a span. Right? So, and in particular, it's a span that points to A and B. So I want this category, you have object spans like this. Because that's what this definition is talking about. So we want to have diagrams of the form Z, A, B, Z, A, and B. So these spans, the end and A and B. So the Z is completely arbitrary, as are these two maps. So it's just two maps like this that show this guy and end and A and B. Okay. So those are the objects. Now we can ask, or you should ask me, what are the morphisms? So the morphisms, well, can you guess, looking at this definition? Yeah.
It'll take you from the diagram that's Z, CA, CB one, to the one that's A cross projections.
Yeah. So if this thing is an object in our new category, and this thing is an object in our new category, there's one thing that I haven't accounted for, which is this arrow making these two triangles commute. So we want that kind of thing to be a morphism in this new category. So morphisms are going to be from, so we need two objects. So let's say we have one object like this, and one object like this. A, and B, call this YA, YB. So we have these two objects. This is one object, this is one object. And the question is, what is the morphism between them? I want to say now that a morphism is something like this. What should I call it? To be F. That makes both of these triangles commute. So it's basically this, except I'm not asking for uniqueness yet. It's asking uniqueness in a second. Okay. Do you guys feel confident that it's a category? Or should we talk about it? So like, what's the identity?
Along the same the identity function I can see, the identity morphism. I guess
Yeah, let's talk about it. So, the identity in a category, so for identities in categories, we need that if this object and this object are the same, then we can produce a morphism between them. So, for identities, we need that if we have two objects that are the same, so the top and the bottom are the same, then we need to be able to put a morphism here, right, from the underlying category C. So write this, this diagram. This is an object of our new category, CAB. Also this is, and this is a morphism in their category, but this is a morphism coming from C. So hopefully that's clear. So all of these morphisms, individual morphisms, are coming from the underlying category C. So in order to produce an identity, we have to come up with a morphism here from C that makes both triangles commute.
Just the identity for C.
Yes, exactly. So we put the identity for C here, and it makes both diagrams commute because of the laws for unitality that are part of the category, so we get identity. Okay, and what about composition? So let's say we have one object in our category that looks like this, and one that looks like this, and one that looks like this, and we have two morphisms. I don't know why I drew F pointing up, but obviously it's symmetric, so I'm going to draw it pointing down now. So say we have two morphisms, F and G. Now I need the composition, so I need to take this kind of diagram. So the composition should take a morphism from this object to this object, and a morphism from this object to this object, to a morphism from this object to this object. Okay, so let me draw the outline first. So we're going to have Z. Yes,
It'll be FOG, which will be defined because it's a category.
exactly. So we can put G circle F here, the composition of these two arrows in the underlying category C, which we know exists because the underlying thing is a category, and it's easy to check if these two triangles meet. So maybe this also helps to address some of the questions from last time about like weird categories like set up. Right, so we took set and we now produced a new weird category set up. Now we're taking something C, like which could be set, and now we're producing another weird category. Yes?
I'm slightly confused about what it means for a category to have an object as a diagram. Like, what kind of mathematical structure is a diagram?
So, what do you mean by mathematical structure, maybe?
Like, I guess, I'm assuming you don't mean literally like it's a picture, it's
Yeah.
objects or pictures. Like, what mathematical structure comes with the diagram that makes it into an object in a category?
You could say that the objects, if we say the objects form a set, which I said I wanted to know much about, but let's say that the objects form a set. So in this diagram, we have three pieces of data. So we first need something like an object in the underlying category. So we're going to have a triple here, that's an object in the underlying category. And we're going to have something, we're going to have these two maps. So we can write in that color notation like this, such that Z is in op C, ZA, I'm kind of running out of room here, is in ZA, sorry, this is really messy, and ZB is in ZB. If you like dependent type theory, this was a good thing to write as a dependent product. Okay. Yeah, does that answer the question? Okay, so, where was I? Okay, so we're checking that this forms a category. We still need to check that this identity that we decided on is left and right digital, and that this composition that we decided on is associative. But you can believe that that's easy to check. It just follows from the laws for the underlying category C. I don't think that as an exercise. Okay, so we have this new definition of category, and I'm not finished with, let me now erase this is the details. So continuing that definition over there, because I'm trying to still define the product in a different way. So, product of A times B is the terminal object in this category that we just defined. So again, I'll leave the details to you, but maybe we just talk through the most important ones. Okay, so can anyone tell me why these two definitions are the same? Maybe in particular, how you get these three pieces of information out of this characterization. Yes.
The intuition that I have is that from the pair, you aren't guaranteed to be able to build back up the source of the pair, but that is very.
Okay, so let's think about what the definition here is asking for. So I just want to think about how this definition implies this one, like how the data of that one gives us the data of this one. So first we need an object in our category C, C times C, and we need these two morphisms. Okay? And those three things, they form a span. Okay? Because It's this thing. They form a span that ends in A and B. This is the category of spans that end in A and B. So first of all, if I say that there's a terminal object, I'm at least saying I have an object in mind, the terminal one, which is going to be this span. Make sense so far? Okay, so I have a particular object in here that is going to give us this data consisting of the first 2 points. Another question is how to get this kind of property. So now in this kind of property, what we see is that, okay, we have our terminal guy. We have another object in the category. And by virtue, so we're assuming this holds, and we're trying to produce this stuff. Okay, so by virtue of the fact that we are assuming that this thing, this span, is terminal in our category, given any other one, like this one on top, we get a unique morphism. Okay, and then I think that's exactly what I wrote. Yes?
Is it also the initial object, because isn't the definition like symmetric? So,
No, it's not symmetric, so we're going to talk about that in a second.
Oh, okay.
Yeah, good question, no. Yeah,
So is it good to sort of think of the spans as like kind of anchored at the center thing that's playing with the brain? It's kind of a pleasant question, but I ask because no, never mind, I forgot.
okay. I'm not sure what anchored means, so maybe if you ask me, I would say these guys are kind of anchored, because all of the spans have to end in these. And the object in the middle can vary among the objects in one category. Yes?
Sorry, I'm very confused with this definition here. We're saying that the product of one thing, but then up there, we were saying that the product of 2 things and B.
Yes.
And we're also saying that the product is the terminal object, but up there, we were saying that the product consists of the object and also some morphisms from the object.
Yeah, so this category, its objects are, now it's hard to read if you do the rest of it, but its objects are spans like this in the original category. So its objects are triples, like over here, of an object in the original category and 2 morphisms like this. Does that make sense? So one object in this category consists of these 3 things in the underlying category, in the original category. Yeah.
So let's call the product let's call the terminal object for a second. The fact that it's in CAB tells us that it's got the projections, and the fact that it's terminal tells us that everything else that comes to A and B will have the morphism to the T.
Yeah, exactly. Okay, yes.
Why is it unique to them?
Well, it's a definition, so I'm allowed to make up whatever I want in definition.